Hey, welcome back for part two of our walkthrough on how Transformers work. This time, we're going to be letting somebody else do the talking for the most part. Well, I'll I'll have my piece. Um, so there's a video by a YouTube creator called Three Blue One Brown, and he tends to do a lot of work making very visually accessible explanations of super complicated math concepts. Um, that said, I'm still around to help clarify some things and add additional details. But when this he released this just last week, this is a very new development. So at time of recording, of course. So I mean, he's really knocked it out of the park. I'm perfectly happy to present his work here. But the idea of how you're going to use this video is as a companion. Um, there's a lot of so there's some technical reasons of how I'm recording this that make that a little easier on me, but also I was going to just play his video inside this video, but I should be driving his traffic. He did good work. He deserves YouTube views. So the way you're going to use this is go through each chapter of his video, and then come back here and hit play on mine to fill in the gaps. I have prepared a document. Um, three. Oop, well, once again, I've made my situation a little messy. I should make this more clear. So this is the three. How do I close this? Save them. That's fine. Okay. So I'll try not to double click the dang thing. This is here I have the video, right? I'm gonna have it pulled up so that we can I can like reference parts of it, but I'm not gonna play it and like replay his audio. So here's a document that I have. I have a lot of notes prepared. Ugh. Once again, what have I done? What have I done? Oh no, now it's all gone. Here, we'll get back. We'll get back. I'm allowed to be a fool on camera. Close all. We got it. I mean, just clicking it once? No, clicking it once doesn't do it. All right. Jeez. Taking it from the top. Or the middle of the top. You get the idea. This video is incredible. He will do a great job of walking you through the fundamental ideas of what's going on um, in each of these like steps of understanding the model. There's more videos after this, and there were some before it in the series, in his particular series. So we're jumping in at chapter 5 to understand specifically GPT, and he does a great job again. And I will be here recapping things. So the idea is read each of these sections slash watch video for each of these sections. After each of his chapters, and I'm here to add additional cognitive scientist insights, additional app developer insights, additional just like clarifications I think might be helpful, because as he does stay extremely what's the word here, accessible, I think I used before. He also recognizes like some of these things are still hard, like they're still like you get a little swimmy in the details. He'll pull up out of those details and make clear like the most important things to sort of grasp in an area. But it's inherently complicated stuff, and I think that between him and my own insights, I can help give you an even stronger take after you see his incredible visualizations and such. So it has these chapters: predict, sample, repeat, inside a transformer, chapter layout, which is just a quick, he does kind of what I'm doing here. Deep learning basics that he sort of recaps from a different area. We'll talk about how word embeddings work, and then how more complex abstract word embeddings might happen, and then how we get words back out of embeddings, and then a little bit about how tokens are selected. This will make sense, of course, as each of those chapters rolls through. So I have notes here, and what I'll do is I will pause recording, and I'll even watch a bit of the section myself just to sort of retap my mind, and then we'll meet back here after you've watched the first section of his video, predict, sample, repeat. It should look like this. GPD stands for Generative Pre-trained Transformers, like the first line of the video. So I'm going to pause, and when I'm done refreshing, I'll come back and tell you about my notes here. Pausing video here. Okay, we're back. I also whipped up a little quick graphic there to help. Go watch the video. I'll be putting that up over and over. So I'm resizing this. What are we seeing here? I think this is a great intro to the basics. You know, we give it words and it figures out the next words. There have been a lot of versions of this over the years. You know, not just Transformers producing one token of words at a time, but even older models. So about the probability distribution of words, I wanted to add some ideas here. So he says that, in fact, in this segment here, I have it paused at, you know, you can see they're selecting from, here, let's see if I can pinpoint it. Well, it's going to try and load a bunch of stuff. Okay, so the model is selecting from a possible most likely next word. And it's funny because this feels kind of reductive, but we also speak linearly. You know, it's not just a words calculate. We have to do the same thing, right? We have to produce one token at a time to make sense. But to help you build an intuition on like why, you know, okay, we're just producing one word at a time. Is that what is that going to amount to? And the reason this is powerful is because the distribution of the words that could come next, right? There are dumb ways to build that distribution, and there are super complicated big data ways to do it that inherit a lot more of the complexities of language and knowledge itself. So the dumb way is what you might have heard of in the past as called a Markov chain, where it's just you take all the text, you see what words come after which words, and for each word you pick the word that's most frequent that might come in the text, or maybe not most, but just raw frequency. And those produce funny example, like ridiculous looking text. See if I can pull one up real quick here. I do have a little on my own website. Let's see if I can. That's Kiln, but I can swing it. Babel, yeah. So let's say we have a Dr. Seuss. You can. This is a little tiny app here. Let's see if I can zoom that a bit. There we go. Ignore the child video. It's funny. So this is a Markov model. The input text was just this Dr. Seuss poem, or book, maybe. And all it's doing is counting up which words come after which words. And when you go to generate text, it just it looks almost like human language. And I know you'll be your day. That scare you will fly, a better break, or the best. It's Seussian in shape and like tone, but it's dumb as rocks, because all it's doing is just taking a word from one word to the next. It's just taking a distribution of like the most likely words in language, regardless of context. The key here is that context adds a ton of information to this situation. So this is the dumbest language model you can make, right? It very lightly apes the way that human language works, but ultimately it's a really pale imitation. Transformers go through the trouble of shifting this distribution of likelihood of what word should come next into the realms of things that actually have deep context understanding, semantic meaning, right? So that's the game we are playing here. The idea of producing one token at a time is very old. and back when we were doing the dumbest possible models. Now we're in a different era, and what we're doing is what we're seeing is these distributions get more and more intelligent. That's the idea. So that gets us there. Also, notable in this section was seeing GPT-2 versus GPT-3 doing the predictions was quite fun. Um, like you can sort of see the side by side. Let me see if I can find it real quick. The side by side comparison was just interesting. But yeah, okay. So now we'll do the next section, and I'll go back to the Go Watch panel and hit pause. See you in a few. Okay, so this section's good. We get into a little bit more of the details of how the pattern sort of goes, right? Again, everything that you're seeing is like he's going to gloss over a lot of the middle bits to give you the overall shape of some in and outs. But the basic steps is we're tokenizing the text strings into tokens. We're putting those each into a big number vector. Those big number vectors get changed so that their context changes with the attention mechanism. So like those big vectors get warped, they get distorted, and then we encode them in the neural networks, and then we repeat that step over and over. We do the attention process and then put it into a more abstract form through a neural network. Do the attention context process, more abstraction. So edit, abstract. That's what the layers roughly are doing in a transformer. Now, I want to have this quick aside. Why do vectors work at all? Like, we're talking about using just throw 1,500 numbers at a word and that can capture its meaning. What are we talking about, really? Now, an issue here is we can't go too deep unless we hit the philosophical grounding problem. This is a classic in cognitive science and philosophy, and the brief version is it's really hard to explain why any words have meaning, right? They are all completely arbitrary symbols. The word cat does not resemble a cat in any way. It's C, A, and T. Those resemble phonetic forms, sort of, that we've decided on. But ultimately, cat. Why does that mean animal that we all, see internet pictures of every day? Bridging the gap between how a symbol becomes grounded in reality is a hard philosophical problem. Now, the reality, though, is that you can get pretty far with understanding most semantics as the relationships between things. So dog, for example, is associated with a lot of other ideas, right? There's a measure of closeness to how it's associated to many ideas. It's furry, has legs, it's a mammal, has bitey teeth. But cat is related, even though in some stupid dichotomies we're like cat versus dog, but really they're so close on the animal kingdom chart that it's not even funny. So those are some close ideas, concepts, words that are close to dog. There are also things that are not as close to dog, like banana, asterisk, spelunking, cannoli. These are just words that are also in our language that aren't aligned very well with dog. They don't seem to have much bearing on the concept of dog. And when you get to this idea, now you start to see why if not all meaning can be construed in this exact same way, but it's pretty important because relationships between things are almost measurable. I mean, you can see from averaging statistics of the way humans wield language in various ways that things have meaning. And that's what we're capturing here. That's the whole point of this, is that you use these big math blobs, right? Like the 1,500 vectors a dimension vector is not, that's just a number that works, right? Like it fulfills the best needs. You could have 20 million, you could have 5, you could have 400. Like the number of dimensions in your vector is really just you setting aside how much space do I think I need to understand the richness of the relationships between things in this language. and 1500-ish is where we've landed with these. So yeah, it's a big weird cloud of numbers, and that can be hard to sort of fully grok, but that means, I mean, this is how we get them into a place where they can represent the relationships between things and not just the things themselves. So we'll go ahead and do the chapter layout. It's very short, but just to keep the form of this going, go watch the chapter layout, and I'll give any tips on that one. I don't think I have any. See you in a minute. Okay. So what was I going to say about this? Oh, we're going to go through all of these sections just because I think they have value. And especially because a lot of you probably, this is your first time watching this, so you haven't looked at the old stuff. And I want to help give some guidance on this. Now, that said, wait, did I have another thought here? Yeah, we'll hit them all. So I guess next, go tap into the next section at 720, the premise of deep learning. Okay, I'm back. So you've now watched the premise of deep learning section. Yep. So this is, sorry, my mind is blank right now. Right. So first I want to just highlight, I think I used a slightly different definition for machine learning earlier in the same short course, but I like this one better. So any model that uses data to determine the model's behavior. I can use, I can program something pristine and specific from scratch, but when you're using data and then tweaking your parameters in your program based on observations from the world, that's machine learning. And I think that's a strong way to put it. I didn't make that as clear before. So, okay, a distinction I wanna touch on because it has good value. He did a great job with it. I just want to really drive it home. So, weights and data. Weights in a neural network are static. These are the things these are what determine how information will flow through the neural network, right? So it's like, think about the slope, like if you're going down a slide or maybe a ski slope or something, and the way that the curves and things bend as you're going down the mountain, that is, you can think of that as the weights that they determine how things flow through this environment, through the neural network environment. The data is whatever the pattern you are trying to push through is, right? So the activation of the nodes in the network, the weights will determine how one set of activations will flow into the next set of activations until blue out the far end of the transformer, for example, we produce a token. So as it flows through the network, getting transformed by weights, right? So when we train a model like this, any model like this, we are building their weights. We are building the shape of their brain, the way that they process information. When we use models to infer and predict the outcome, this is where we're putting in input data that we want to be, processed fully, as opposed to used to train the weights. So when we're inferring, the weights are static; they don't move, and that is everything we do with GPT is infer, where it's all static. I really just wanted to highlight, I love this knobs and dials intuition that he's using here, the way to think about parameters. GPT 3.5 might have 175 billion dials, but that's what it is, ultimately. Like, those are numerical values that will determine the behavior of information coming into the system. So this is a great intuition. Keep this idea of the knobs and dials fresh in mind as you proceed in your life of examining this stuff. Oh, I only just noticed I have part of my Spotify thing's visible down there in the whatever. That's silly. And then backpropagation, I guess just a quick sketch of how this works is the basic idea with backpropagation is to give a stronger intuition of this is like, you have a network and you give it some input and you know the answer. You know what word should come next. So you give your network, maybe it's just fully random. It doesn't know what the heck it's doing yet. You give your network some kind of input and it'll produce something. It'll be like, beans, and you'll be like, no, that was way wrong, and you now punish the network. You adjust those dials throughout your neural network to diminish the wrong answer in a way. And then if it gets the right answer, you do the same thing, but you are enhancing, moving things to make sure those right answers happen more often. So backpropagation is just the idea of when you have something that you know the model should be doing, you can give it enough to get to the point that it needs to predict something, and then change the weights based on whether it was right or wrong, and to an extent, like also how right and how wrong. But that's all nuance of the actual training, just to give you the idea of how these things tend to happen. So that's how it can learn from data: is it observes something, and then when it gives us the right answers, we reward its structure in the weights, and when it does something wrong, we punish it. Sorry, I'm getting distracted by what we're doing here. So, premise of deep learning. Yeah, okay. So now move on to word embeddings, and we can keep this going. Okay, I'm back. So, the word embeddings section. This is great. We're seeing how at the start of this process, the words we are giving, the tokens. Now, to give a quick distinction here, tokens are mostly words. They do also feature subwords, like parts of words, and smaller chunks, even just individual letters, right? Those are the kinds of things that a token can be. Maximally, a whole word; minimally, a single letter, and lots of chunks in between. So this is why you can actually give it something that it hasn't been trained on. You can define new words. You can, when you're talking to it, you can say like, "Hey, let's think about this. I'm trying to name this thing, this new whatever product or something," and it will effortlessly adapt a new word into its vocabulary because it knows how to handle small chunks and individual letters as parts of words. Just a neat thing. So I think that there's some very useful intuitions I can impart when it comes to understanding these high dimensional vectors. Remember, these vectors are big number blobs, right? Each word has 1,500 numbers that associate to its semantics. Okay, we're past that at this point. We can basically agree that there's some way of measuring semantic relationships with big blobs of numbers. Ways to think about big blobs of numbers. So first, what are the basic intuitions about vectors? We live in a three-dimensional space. That means that there are three dimensions that make sense. There's forward, back, up, down, and left, right. There's other versions of this depending on if you're going to use like polar coordinates or something, but just bear with me on like the normal three-dimensional space, X, Y, and Z. These are the things that we can actually like see and perceive directly in the world. I'm in a space that has it might have weird angles, and there might be a strange roof angle here, but it's still just kind of a box, and it has three extensions in space. But three tends to be where our brains stop being able to, measure things. But to show that we are still extending beyond that, and we have ways of understanding it, you also know the fourth primary dimension of space, which is time. The 3D world has a state right now, and then in another moment, it will have a different state. And then another moment, it will have a different state. That is a dimension, right? Now, beyond space and time, there's tons of dimensions. Colors, partial colors, red, green, and blue are each dimensions. How loud something is, what's the temperature of the object that you're touching. There's measurable dimensions of all things, and not all things, but in many types of things, right? So these big vectors are doing something in the space of saying like, okay, there's a lot, like in the video. Wait, have we gotten to that point with the like kings? Yeah, right, we just did this. So the some of the directions in these 1,500 vectors, or maybe combinations of directions, themselves have kinds of meaning. And it might not be something as simple as a red to blue spectrum, for example, but it's still something that captures a meaningful relationship between things. So just to give some basic ideas on vectors. And then also, when they're showing these cool little 3D vector diagrams, something that's useful to think about is like, remember, these are big blobs. These things are about 1,500 dimensions long. And we can't visualize that. We are humans. We're stuck in 3 dimensions. So we got to pull things down. But what we're seeing is sort of a shadow of it, a projection downward. So what exactly is a shadow? A shadow, if you think about it carefully, it's a 2-dimensional projection of your 3-dimensional self onto the plane of the ground as caused by, light shining on you, us blocking out light. Some of the picture of that 2-dimensional silhouette of yourself, some of the information is still there. Like, you might be able to see what you're wearing, or I can distinctly determine limbs depending on the angle, but a huge amount of information is lost. So when we think about these vectors as things that we should be able to sort of like wield in our minds a little bit, just remember, they are too big. That's kind of why we have to rely on a system to handle the big math here. Like, it's not that these are not things that are easy to grok and like you just have to be a genius. No, your brain can't do 1,500 dimensions at once. We're lucky to get 3. So whenever you see these things, know that it's super reduced, and remember that it's a shadow. And then finally, for this section, it crosses the mind that it might be a little confusing. How do we even get the embeddings in the first place? They sound like they're numbers that we already have established when we go into the transformer model. And that's right, because training embeddings themselves is a machine learning process. You give it the data set, and it sort of learns what numerical vectors maximize and minimize the amount of like relationships that it can find, right? It's a wiggly process until it eventually settles on a good set of dimensions for the words that exist. So they're trained, they can be trained on their own. I'm sure OpenAI is training them for all their own stuff, right? But you can train embeddings separately from whatever transformer model you're using. So yeah, and they're meant to sort of define the space, and like I said before, you could do arbitrary different numbers of embeddings. You could do different sizes of dimensions of embeddings, but the ones that we land on in the current moment of GPT world is these 1,500 dimension ones. So yeah. Let's see. So as they train, they sort of solidify, the embeddings solidify into a good dimensional space. You could retrain them a whole different way and they might solidify in a different way. You could give it a different set of data and it would sort of arrange slightly differently. But overall, it's about sort of anchoring this to something that is somewhat stable. Okay, now go to Embedding Beyond Words and have a look. Okay, so the main thing I want to talk about here is how cool the attention mechanism is, and like why this is such a clutch piece of the design. So this is where we finally get into higher abstractions. We talked about basic embeddings to give us sort of the basic semantic meaning of words. Now we have the in-context meaning. So this is sort of the quickest way into understanding, like, oh, this thing is encoding more complex and complicated abstractions because of all these deep network layers in the model, right? Because it has a lot of neural network layers bubbling up new abstractions. So in the Macbeth example, it shows how without any of the word, none of the words Scotland or murder or even Macbeth were used, right? But the surrounding text, this raw script of Macbeth that it was presented with, just completely activated those same patterns, because that's the space that the text of Macbeth takes in this semantic world that it's absorbed, right? So it sees a piece of Macbeth, it instantly gets the idea that the king in question is a murderer from Scotland, and right in the embedding vector, right? It doesn't have to like look that up. It's just, oh, right, these words coalesce around king to give that meaning to it as well, right? The words from Macbeth, those vectors from Macbeth's specific word combinations and their abstractions maybe, imbue the word king with the properties of being from Scotland and being a murderer. That's the vibe here. So this power of abstraction is due entirely to the attention mechanism. The next video of his is on that. I recommend it, but again, not part of the core here. To give you the quick version of attention, though, is the attention mechanism is what's changing the meaning of all of the embeddings to be more accurate, you might say. It's not just like, okay, here's flat meaning of a bunch of words and good luck. It's saying the user wants to say something here. They are communicating something here. The text is communicating something here. Therefore, we want to tune the meanings of words until they really grasp the deeper structures than just flat surface level understanding. So you repeat this process over and over. And so you run this attention, you update, you say, okay, based on these basic structures, I think these words have these new meanings. And then you go a layer deeper through a neural network. And now you're in a little bit more abstract territory, because neural networks tend to do that. They help to filter down into even more higher level abstractions. So you do this a bunch in the transformer model, in all the most powerful ones especially, and you get to a place where really deep abstractions have been applied using this attention mechanism to the entire structure. Right, so the deeper those networks go, the more networks in a row you get, the more abstract the structures it can imbue the text with. That's the cool thing about this attention mechanism. Okay, go now and check out unembedding. Okay, back. This is short. It was succinct enough, I think. But to make it extra clear. It's the same thing as when we take our text and embed it into these big vectors, but kind of in reverse. We take the patterns of the vectors we've been updating and abstracting and making more and more and more refined to the point of understanding to not get in trouble with the philosophers. And we try to find a word vector closest to the one that should come next in order, right? Remember, that was the whole point of that's the whole structure of training these models is, here's a bunch of text, what's the next word? And the next word that it wants is somewhere near the embedding vector they're not embedding vector, but the vector that it has resulted in at the end here. So you get a possible set of words according to our needed vector. You get this set of words that are all closest to that. So that came out funny. Let me make it extra clear. You do this process and you end up right at the end. It's time to produce a word. You've done a lot of work to make sure the understanding is nuanced and refined to the point that you might understand a lot more about Macbeth, for example. And now you are in the space where, okay, I have a big vector, I need a word. So this big vector is where we're at, and then we find all the words that are the other word vectors in the space that are closest to it. And thus we get the list of possible embeddings, or no, possible tokens to produce. So, yeah. The softmax section, I don't want this to be too long in the tooth. We've already gone quite a ways. I'll just leave that as optional. I think it's worth watching. It's like 5 minutes, 4 minutes. You know what? I'm going to call it and make it optional. Again, this text will be available to you. You can actually see it right here. This is just some stuff about how temperature works and stuff. It's cool, but no fuss. I'm going to go ahead and say that we don't need to head back to the video, but I do have some closing remarks and thoughts. So I would say definitely keep watching the video. Oh, we've done it again. There we go. Definitely keep watching the video series if you're interested. He continues to do a great job. The second one is up, so chapter 6 on the Transformer stuff is up, and chapter 7 is coming soon. And the whole series is really good. The whole deep learning series is great. You can pause it if you don't understand something. You can look it up, whatever. So enough plugging for him. I think he's doing a great job. The quick recap is like transformers are these things that distill meaning from input, turning its constituent words into big math objects, right? It has lots of layers of iteration and abstraction, so it can really grasp patterns, pattern recognition, and deep structures using its deep learning networks. And these more and more esoteric patterns of language, it's able to pick up. So now they can talk to us in streams of tokens selected based on what makes most sense in a really intelligent way, one after the other, right? So that's why the tokens flow back to us, right? So really, this is how we're able to engage in these useful back and forths with these tools. So yeah, I hope that you now have a pretty solid grasp of how they work. Look, when I first watched this video, I learned just as much as I was excited to see. I was already like, oh yeah, I got that one. Half the time I was learning something new. This is not easy stuff, and it's not, and I don't even mean easy. It's just obscure. You're not going to encounter this stuff in your regular everyday life. That's why I'm trying to like get our attention corralled onto it. And this is a great filter by which to do this. I'm really happy with his video. I hope you had a good time with it too. I do want to stick to one last big idea about what some of the knowledge we've acquired here today means for how you interface with these models. And this is the phenomenon called autoregression. So, you got the basics here. The main feature, the main structure of this thing is that it produces one token at a time by looking at what has just been said, right? Fundamentally, that's the basics. That means that this model is what is called autoregressive. So really that just means I can't look forward in time, I can only look backward. So it can't work, it can only work with words that it has already seen in context or words that it has just generated in the same context, in the same call. Functionally, we can maybe relate to this. Have you ever, spoken a sentence and thought, like, where was I going with that? You get a little turned around in your own words. So humans and AIs can both get garden pathed on trying to produce words. But this feature causes some pretty major limitations because of the inherent structure of how this model functions. So let's talk about those. First, it struggles to naturally plan ahead on its own without any scaffolding. For example, these AIs suck at jokes. You can try it out yourself. It's a well-documented phenomenon. You can just Google it and see some of these examples. But the AI cannot tell functional jokes when you just ask it point blank. It will do something that looks like a joke, and then it'll get to the punchline, and it will always just face plant into the sand. Because a joke, structurally, conceptually, jokes have a structure. They require some kind of setup and then some kind of punchline that relates to that setup. And usually some kind of twist or some kind of inconsistency is what leads to that little snap of humor. But the idea is you have to set the thing up and then deliver. One of the most basic, send up payoff structures that we have. Because the AI does not know the ending ahead of time, it can't, remember. It can't see into the future. It can only look, you saw how it computes each single token, right? So it has to produce one word at a time. It can't possibly deliver on a good setup because it doesn't know the punchline yet. And so in general, what this means is that while the model will do pretty good in a lot of ways, if anything you're trying to do in sort of a single shot, like one go, if it requires any kind of planning, it screw things up pretty easily. right? So be aware of planning when you're using the models. And a really useful fix for this is an idea that's been going around that's called the prompt. Include this in your prompt. Let's think step by step. Super useful because what it does is it gets the AI thinking in terms of collaborating with you, like with the let's, but also the step-by-step process. And the word think encourages it to express its thoughts, right? So expressing yourself clearly in a step-by-step manner means you're going to be breaking things down. It means you're going to be explaining what the plans might be. It means that you'll be generating text that will sort of scaffold the rest of what you're doing the entire time you are doing it. So it doesn't mean you can completely avoid its kind of failure to plan type stuff, but by having it always producing its train of thought and help keep it sort of on track for what it should be doing, you're keeping the ideas that will come in the future within the realm that it can still see it. You see what I mean? This is really powerful stuff for understanding when you're working with prompting. So keep this one in your back pocket. It requires an understanding of why this, about the structure of the models and such, but it also, you got a little bit of a fix here to help you understand what to do. So it can help avoid issues that come when it has no idea what the future holds. Whew, wish I had the same. Okay, so that's it. It struggles to plan ahead, and the next one is what you may have heard already about the idea of hallucinations. Models will just start making things up sometimes, and there is the possibility that they're just like, in a basic sense, wrong. Like they don't have the knowledge. They don't know the knowledge. In other times, they just get sort of derailed, and there's no way for them to get back on the rail, and we'll explore why that is. So imagine the model picked a somewhat strange word, like through some weird oddity of like the temperature settings, or maybe the way that the training, there's some weird little crease in the knowledge base that's kind of weird. Let's say it got something wrong, like it was talking about the weather, but it tossed the word bananas in, right? The problem is, because it is exclusively structured around, okay, I need to look at what I just said and produce things that logically follow from what I just said. It's getting itself into a place of tension where now that this word banana is in the context window, it has to fight sort of there will be two distributions fighting for what token should be produced next. The distribution of, hey, we were talking about the weather, and the distribution of, yeah, but the word banana is right there. So what happens is it will now continue along as if the word banana should be there, even if it sort of erroneously injected it. Now that doesn't make much sense for talking about banana and weather, but imagine instead that you were saying, like, you were at the edge of its knowledge and you asked it something and it tried to produce a token that might be real, but maybe it wasn't very sure. And now it's produced a token that's sort of junk, but now it has to proceed as if it believes that token. It's not going to stop at each token and verify what it's doing. That's where you come in. So these hallucinations will happen. The fix for that is one fix, and there's lots of ways around this. Keep your eye on prompting, but the self-critique model. So yeah, it's bad. It will get itself on a weird little track, and it'll wander to a dead end, and it'll die on that hill. The cool thing is, if you stop and ask it, hey, what was that thing about the banana in the weather? And you ask it maybe to explain its reasoning, or even just blankly assess what you just did. To think about the words you just wrote. A lot of times, it's great, like we talked about just now, it's great at reading existing text. It's not great at knowing what should come next. Not next. It's great at knowing next, but not necessarily knowing what will come far from now. So, so what you're doing is you're helping it by saying, like, look back at what you just said, reassess that. And typically it will really immediately catch its own mistakes. Sometimes it'll double down. If it's still fishy, you keep pressing it, right? But another option is to get it to cite its sources, or at least give you a way of verifying the information it's providing you. So having a system of understanding, like, look, I know this thing will sometimes produce these hallucination situations, and knowing that you have a way sort of to push back and maybe get out of those situations. That's one of the key take homes. Okay, I've eaten enough of your time. Thank you for coming along. Really like this video. Really glad I could add a lot of new details. I'll be publishing this along with the video. So that's it for this time. Take care.